Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, so we're going to be factoring expressions here. Factoring is something that some students will pick up easily, others not so much, but if you persist, it is well worth it because you need to deal with factoring. Algebra 1, geometry, algebra 2, pre-calculus, calculus. So this is a concept that just keeps coming back. So let's hope we get this right here. Example 1. Use the model to answer the following questions. So we have a rectangular with a value of 5. We have another rectangle with a value of 5. So it said there are two rectangles of 5, or 2 times 5. There's a rectangle with a value of 3, and another one with a value of 3. So there are two rectangles with a value of 3. So they're saying the 3 is represented 2 times, or 2 times 3 is 6. So then it asks these questions about the model. How many 5s are in the model? And there are 2 5s in the model. How many 3s are in the model? There are 2 3s in the model. What does the expression represent in words? So I want you to represent this. What does that expression mean? So I would say it is the sum of 2 groups of 5. Let me not use numbers in my sentence. 2 groups of 5 and 2 groups of 3. I did it again. No numbers sentence. Okay. THREE. There we go. So the sum of 2 groups of 5 and 2 groups of 3. What expression could we write to represent this model? Well, the expression is given to us right here. So we could say 2 times 5 plus 2 times 3. I'm going to rewrite that without an x. X looks like variables. We are now using variables. So I'm going to use a dot for times. 2.5 dot. Okay. Now it says use the new model in the previous model to answer the next set of questions. How many 5s are in this model? And I see one here. I see one here. So there are 2. How many 3s are in this model? There's a 3 here and there's a 3 here. So again, there are 2. What does the expression represent here in words? So here we're adding 5 and 3, so we could say 2 groups of the sum of 5 and 3. What expression could we write to represent this model? We could put parentheses around 5 plus 3 and add it to another expression of 5 plus 3. So we're just putting a plus sign here and putting parentheses around those. Or we could say that there are 2 groups of this one group of 5 and 3. 2 groups of 5 plus 3. Okay, so we're leading up to something here, so be patient. C says, is the model in part A equivalent to the model in part B? So the model in part A, if we were to add all of this up, 2 times 5 is 10, 2 times 3 is 6, 10 plus 6 is 16. If I come down here, I get 5 plus 3 is 8, plus 5 is 13, plus 3 is 16. So they both add up to 16. So is the model in part A equal to model in part B? And the answer is yes. Okay, because let's see, what I could say is 2 times 5 plus 2 times 3 equals 2 times 5 plus 3. So as you can see here, this has a 2 being multiplied. This has a 2 being multiplied. So that is what's called a common factor. So 2 times 5 is 10. And factors of 10 are 2 and 5. And 2 times 3 is 6. Factors of 6 are 2 and 3. So the common factor of these two numbers is the number 2. So I can factor out the common factor. What relationship do we see happening on either side of the equal sign? Okay, I'm going to bring this one in so not to right. Okay, so it says on the left-hand side, 2 is being multiplied by 5, and then by 3, before adding the products together. On the right-hand side, 5 and 3 are being added first and then multiplied by 2. So we're doing orders of operations here. E says in grade 5 and in module 2 of this year, you have used similar reasoning to solve problems. What is the name of the property that is used to say that 2 times 5 plus 3 is the same as 2 times 5 plus 2 times 3? And the name of the property is, so you already know this, the distributive. So we're distributing the 2 to get 2 times 5 plus 2 times 3. Okay, so example 2 says, now we will take a look at an example with variables. Discuss the question with your partner. So this was an example that you were supposed to do in class together, so if you have not done this yet, pause the video and come back and check your solutions. Okay, so what does the model represent in words? So we have A plus A plus B plus B. A plus A plus B plus B. Okay, or we could have said 2 A's plus 2 B's. Or we could have said 2 times A plus 2 times B. What does 2A mean? Okay, it means there are 2 A's. Or 2 times A. I don't want to put a dot there because it looks like times. 2 times A. How many A's are in the model? 2. How many B's are in the model? 2. Now it says what expression could be written to represent the model? A plus B. A plus B. How many A's are in this expression? First, let's come up with an expression. So we could just take this here and add it to this here. So my answer would be A plus B plus A plus B. Or since we know that there's 2 groups of A plus B, we could say A plus B times 2. How many A's are in the expression? There's 1 here, and there's 1 here. So there are 2. How many B's are in the expression? There's 1 here, there's 1 here, so that is also 2. What expression could we write to represent the model? And that could be a 2A plus 2B. So really what we're doing here is just simply distributing right there. Are the 2 expressions equivalent? In other words, is 2 times A plus B equivalent to 2A plus 2? The answer is yes. Example 3. Use the greatest common factor, that's what GCF stands for, the greatest common factor and the distributive property to write an equivalent expression. So I have an F in this term, I have a G in this term. They are not like terms. So that is what I can put in my parentheses. I want to look at my numbers before I write anything. There's a 3 here, there's a 3 here, so that means there are 3 F's and there are 3 G's. So I can factor out the greatest common factor, which is 3, put it outside. And then 3 times F plus G. So then when I distribute, 3 times F is 3F plus 3 times G, which is G. What is the question asking us to do? Okay, we pause the video and bring that in. Okay, so it says we need to rewrite the expression as an equivalent expression in factored form, which means the expression is written as the product of factors. The number outside of the parentheses is the GCF. So the greatest common factor of 3x plus 3g is 3. Number 2. 6x plus 9y equals. Okay, so again, they want us to factor out the common factor. And if you have trouble with this, do a factor tree. 6 is 2 times 3. So my factors are 2 times 3. 9 is 3 times 3. So 3.3, and then I'm going to circle what they have in common. This has a 3, and that has a 3. And they have things that are not in common, or uncommon, they're different. So they are not going to be part of the factor. So the greatest common factor of these two terms is the number 3. So I'm going to write the greatest common factor outside the parentheses. What do I have to multiply 3 by to get 6x? That would be my other number of my factor, 2 times x, plus, and then I use the 3, I have the 3 remaining, it's 3 times 3 is 9, and I still have the y, so I have 3y. So the greatest common factor is the one I circled, and the ones that weren't common go inside the parentheses with the variables. So this question is asking us to find GCF. Okay, so the number outside the parentheses is the greatest common factor. The number inside are the uncommon factors of each term. Okay. How would problem 2 look if we expanded each term? So I have already expanded it here, so instead of writing 6x, I would say 2 times 3 times x times 3 times 3 times y. And we're not multiplying those two, we're multiplying 4. So 2 times 3 times x plus, got the plus 3 times 3 times 2, not all. What is the GCF in problem 2? Okay. On either side of the plus sign, so if I drew a line down right here, what does this side and this side have in common? 1, 3. So the GCF in problem 2 is 3. So how can we find the GCF to rewrite the problem? The greatest common factor goes outside the parentheses. The uncommon factors stay inside with the sign of the equation, or not the equation, but the expression. Okay. Let me bring that in for you if you want to comment. Okay, so how can we use the GCF to rewrite this expression? I will factor out the 3 for both terms and place it in front of the parentheses. I will place what is left in the terms inside the parentheses. 3 is quantity, 2x plus 3. Number 3. 3c plus 11c equals. Is there a greatest common factor in this problem? So you might look at this and say 3 is 3 times 1, and that factor tree, we never put 1s in our factor trees. 3 is prime. And then 11 is 11 times 1. That's prime as well. So you might think, no, there is no greatest common factor in 3. The factor does not have to be the number. It can be the letter. So if both terms have a c, then there is a greatest common factor. So I'm going to, it says, rewrite the expression using the distributive property. So I'm going to put this up here. I'm going to take the common factor out of both. They both have a c. Multiply it by, and then inside I'm going to put what's left. So if I take a c away from 3c, that leaves me with 3. 3c divided by c is 3, plus 11c divided by c is 11. So we're just, it's distributive property in reverse. That's what factoring is. So it says rewrite the expression using the distributive property. Well, I already did. It's right. Number 4. 24b plus 8. Okay, in this one I have a b in the first term, no variable in the second term, so I have to look at my numbers. So if I do a factor tree for 24, it's 2 times 12. 12 is 2 times 6. 6 is 2 times 3. So my factor tree yields 2 times 2 times 2 times 3. And then if I do the same for 8, it's 2 times 4, which is 2 times 2. So the factors of 8 are 2 times 2 times 2. Now when I go back and look at what they have in common, 24 has 3 2's, 8 has 3 2's, and that is my greatest common factor, so I put them back together. 2 times 2 is 4 times 2 is 8. So I can factor out an 8, put in parentheses, and I just divide. 24 divided by 8 is left over 3, the variable, don't forget that, plus. Now here's where a lot of people make a mistake. If I am going to factor out an 8, I can't put plus 0 here, because if I distribute now, 8 times 0 is 0, and there'd be nothing. So what do I multiply 8 by to get 8? The answer is 1. Okay. Very common mistake to simply write 8 times 3b and forget that I have to distribute the 8 times 1 to get it. Okay, so it says explain how you use the GCF and the distributive property to rewrite the expression in problem 4. So I first expanded each term. I know that 8 goes into 24, so I used it in the expansion. 2 times 2 times 2 times 3 times b plus 2 times 2 times 2. So I showed that in a factor to my left. I determined that 2 times 2 times 2, or 8, is the common factor. So on the outside of the parentheses, I wrote 8. And on the inside, I wrote the leftover factors of 3b plus 1. This is kind of. Why is there a 1 in the parentheses? Well, I explained that already. If there wasn't a 1, if I put 0, there would be nothing to distribute. Not only 24b. How is this related to the first two examples? Okay. I will bring that one in as well as relating. Okay, in the first two examples, we saw that we could rewrite the expressions by thinking about groups. We can either think of 24b plus 8 as 8 groups of 3b and 8 groups of 1, or as 8 groups of the sum of 3b plus 1. This shows that 8 times 3b plus 8 times 1 is the same as 8 times 3b plus 1. And that's the same as 24b plus 8. Okay, so here's an exercise for you to try. Several problems. Do 1A through H. Pause the video. Come back, see how you did. And we'll discuss this. Okay. So it says to apply the distributive property, ready to put the expressions. I have an x, I have a y, they're not common. I have a 7, I have a 7, they are common. That's my greatest common factor. That comes outside. 7x divided by 7 is x, plus 7y divided by 7 is 1. 15g, 20h. I know I can take a 5 out. I'm not going to do factor trees anymore. 15 is 5 times 3, 20 is 5 times 4, so I can take a 5, leaving 3g plus 4h. Okay. Now when we get down to this one, we may want to do a factor tree when we get into larger numbers. 18 is 2 times 9, which is 3 times 3. So it's 2 times 3 times 3 is 18. 42 is 2 times 21, which is 3 times 7. So my common factors are 2 and 3. So 2 times 3 is 6. So I can factor out a 6. Parentheses, my remainder from the 18 was 3. Don't forget your m. Plus 42's remainder was a 7 times their n. And there it is. Okay. Next one. 30, 39. 3 times 10. 2 times 5. So it's 2 times 3 times 5. 39 is 3 times 13. So that's just 3 times 13. Common, 3. 3, parentheses, leftover, 2 times 5, 10. 3 times 10 is 30. Don't forget your a. Plus 13 is my leftover. Don't forget your b. There's the factor. 11 is prime, 15 is 3 times 5, but if you have a prime, you can't factor it. 11 won't go into 15, so my common factor here is the variable. They both have an f, so it's just simply f times the quantity 11 plus 15. F times 11 is 11f, plus f times 15 is 15. When you are done, you should always multiply through and see if it's still true or you made a mistake. Here 13 is prime, 18 is a multiple of 3 and 2 and 3. So a 2 times a 3 times a 3 is 18. But this is 1 times 13, nothing in common. But they do each have an h, so that is my common factor in this case, leaving the numbers behind as the uncommon factors. Okay, this one is 11 and 55. Now if I did a factor tree on 55, it'd be 5 times 11, and 11 is prime, so 11 is just 11 times 1. We don't show 1s in our factor tree, so 11 is just 11, and the common factor of 11 and 11 is 11, so I put 11 here. 55, the leftover factor is 5, don't forget your variable, plus, and remember, you cannot put a 0 here or we will only have 55 in it. So 11 times 1 is 11. So really, if I did a factor tree here, I would do 1 times 11. My leftover is 1, and that way you don't forget. Even though we don't normally show 1s in factor trees. Okay, 7 and 56. 7's prime, so let me do a factor tree for 56. It's 2 times 28, which is 2 times 14, which is 2 times 7. So it's 2 times 2 times 2 times 7. And the other factor, the number was 7, so I'll just put that over there. And obviously that is our common factor. So I'm going to put a 7 here. 7 times 1, remember it's 1 times 7 is 1 times 7. If you did a factor tree like that, then we have a leftover 1. Plus 2 times 2 times 2 is 8. 7 times 8 is 56. Okay, so now it says evaluate each of the expressions below. So I'm going to pause the video, see if you can do this with substitution. They're telling us x equals 3 and y equals 4 and a, and g is equal to 6. They want you to solve these with those values. Okay, so I'm going to substitute in. So 6, x is 3, plus 21, y is 4. 6 times 3 is 18, plus 21 times 4 is 84. 8 plus 4 is 12, carry the 1, 8, 9, 10. I get 102. If I do it over here, I'm going to have 3 times 2 times 3 instead of the x, plus 7, and y is 4. So it's 3 times 2 is 6, plus 7 times 4 is 28. That would be 3 times 28 plus 6, which is 34. 4 times 3 is 12, carry the 1. 3 times 3 is 9, plus 1 is 10. So as you can see, we got the same answer. The factored form is equivalent to the unfactored form. Okay, now I want to plug g in. I want to plug 6 in for g. So 5 times g, which is 6, plus 7 times g, which is 6. 5 times 6 is 30, plus 7 times 6 is 42. 30 plus 42 is 72. And now I'm going to plug the 6 in over here, so I'm just going to put a 6 in place of the g, 5 plus 7. PEMDAS says to do parentheses first, so 5 plus 7 is 12, and 6 times 12 is also 72, so the factored form is equivalent to the unfactored form. Okay, moving along. C, let x equal 10. Pause the video, try this one, come back, see how you did. Okay, 14 times 10 plus 2. 140 plus 2, 142. 2 times 7 times 10 in place of x plus 1. 2 times 70 plus 1. 2 times 71. 2 times 1 is 2. 7 times 2 is 14. And they are equal. Explain any patterns that you notice in the results from parts A through part C. What patterns will we explain or discuss here? Let me bring that. Okay, so both expressions in parts A through C evaluated to the same number when the indicated value was substituted for the variable. This shows that the two expressions are equivalent for the given values. What would happen if other values were given for the variables? Because the two expressions in each parts are equivalent, they evaluate to the same number no matter what value is chosen for the variable. In closing, it says, how can you use your knowledge of the greatest common factor and the distributive property to write expressions? Okay, we can use our knowledge of GCF and the distributive property to change expressions from standard form to factored form. Okay. And in closing, they're giving us another activity to do, so find the missing number in this. So they've done the factoring for you, you just have to tell them what the GCF is. Try it and return. Okay, so what I would do is take 4x divided by x. What's missing? 4. 4 times 3 is 12. 35 divided by 7 is 5. 50 divided by 10 is 5. 18 divided by 2 is 9. 9 divided by 1, 9. I always check the other one. 32 divided by 4 is 8. 8 divided by 8 is 100 divided by 1 is 100. 700 divided by 7 is 1. It says explain how you determine the missing numbers. Okay, I would expand each term and determine the greatest common factor. The greatest common factor is a number that is placed on blank. Okay, I didn't do it that way. I showed you a shortcut, and I divided because that's how you find factors. But what they're saying is expanding each term. That simply means do factor trees. So let's just do one like that. So let's try this one. So if I did 35, 50, and I factor tree this, 5 times 7, 5 times 10, which is 2 times 5. So this is 5 times 7. This is 2 times 5 times 5. I have a 5 in common. So that right here, and the number that was in the tree is 7. That's there. And 5 times 2 is 10, and that is there. So either way you want to do it, that's fine. That is the end of lesson 11. Your problems.